All right, so in this video, I'm going to go through the start, probably just the multiple choice of the 2015 Systems Engineering exam as sort of a refresh of our theory, or how do we look at exams, or what do we do with exams when we're not sort of 100% sure the answer because we can't exactly remember all the theory, but if we think about it logically, we can sort of get there. So what I encourage you to do is either have a crack at this exam beforehand and then look at this video, or have a crack at this exam, and when you get stuck on something, find where I'm doing the question on this video and see if you can follow along, and hopefully it'll make sense to you and you'll learn something, and if nothing else, you'll know that there's a little bit of theory that you need to go back and visit. So what I'll do is I've got this touch screen here, and when I'm doing a question, I will just write, so for example, if I was doing question 1, I will just write question 1 on my little paint pad, and I'm drawing with my finger, so forgive me if it's a bit messy, to let you know what question I'm on. Oh, I shouldn't have got rid of that. Anyway, so let's do the first question. Question 1. A danger or unsafe tag on an electrical device may be removed only by, most of these OH&S safety questions, just look through them and think about what is the safest or the most logical answer, and that's going to be an electrician, right? So question 1 is going to be D. Oop. Cool. Question 2. What type of energy comes from heated groundwater? Right. If you remember, it's geothermal. If you can't remember, let's have a look at the words. Heated groundwater. Okay, hydroelectric. Well, hydro and water, that sounds plausible, so let's put that in the maybe pile. Geothermal. Gee, geo and ground, those have got a lot to do with one another in terms of being words, and thermal and heat, so that's sounding pretty good. Biomass has absolutely nothing to do with heated groundwater as far as I can tell, and neither does solar. So, if I didn't know, I'm sitting here tossing up between hydroelectric and geothermal, and geo, ground, thermal, heated, that's a pretty good bet, right? So question 2, even if you don't remember, is going to be B. Question 3. Another pretty common sense question. So you've built a thing. The next step in the systems engineering process is to do what? So, reevaluate, modify, and document. Eventually, maybe, but it's not the next thing you do. Start a brand new project? Nope. Evaluate and report? You're probably going to do that at some point, but are you going to do it straight away after you've built it? Probably not. Are you going to test it and diagnose it and see if there's anything wrong with it? See if it works the way you like? Yes, you are. That would make the most sense. So that's going to be A. Question 4. All right, question 4 is a bit more of a question, I think. Whoop. Which one of the following devices does not use magnetic fields for its operation? And you've got relay, solenoid, transistor, transformer. So, if you're thinking back to theory and magnetic fields, recall that at some point we got a nail and we wrapped a coil of wire around it. Nail. No, I can get rid of the nail. Anyway, coil of wire. And we put an electric current through that, and that created a magnetic field. In fact, anytime we put a current through a coil, we can create some sort of magnetic field. So let's look at the things that we know about. Okay, so what is a relay? A relay is a switch that is actuated or moved because it has a coil next to it, and if you energize the coil, it'll move the little element of the switch, and so that's magnetic field. Solenoid is a coil with some sort of iron, usually iron plug in it, and when you put an electric current through it, you create a magnetic field and it moves that plug. Okay. Transistor is one of those semiconductors that can act as a switch or as an amplifier. You might recall that it's weird PN junction stuff that makes those work, but you might think, oh, well, I don't know, maybe it's a magnetic field, so let's put that in the maybe pile. And a transformer is one coil of wire, another coil of wire. We put a current through one coil, we get a current in another coil. So that's, and they're not touching, they're not connected. So that is magnetic fields. Please excuse my terrible scribbles. to denote magnetic fields. Okay, so which one, we know that 3 of them pretty firmly use magnetic fields. So the answer is going to be C. It's our transistor that does not use magnetic fields. Cool. Question 5. Now, this is another good question. So the thread pitch of a bolt is 1 millimeter. So pitch and screws and things. Screws are part of the course design, bolts and things, because they're useful ways of joining stuff together, but also because they're, based on one of the simple machines, which is an inclined plane. And so what a bolt is, let's draw a bolt, is an inclined plane wrapped around a cylinder. And so what is pitch in this, sort of words are failing me. In this sort of scenario, well, pitch is the angle or the steepness or something like that, like the pitch of a slope or the pitch of a roof. Draw a little house. Pitch of a roof. So what does a pitch of 1 millimeter mean? Well, it means that if you were to turn this bolt 360 degrees, the distance this plane would, seem to move, because it would be seen to sort of twist. So if it was to turn 360 degrees completely around, that would be 1. For the thread pitches, the bolt is tightened 1/2 a turn. Okay, so instead of being turned 360 degrees, let's say we've turned it 1/2 a turn. And it's turned 1/2 a turn after it's come into contact with whatever it is you are using the bolt to tighten down. So this is bottomed out. So you've turned it 180 degrees. So you've moved this thread, again, you've moved it in terms of the, up and down direction, 1/2 of the pitch, which is 1/2 a millimeter. So the bolt shank, or this part, is going to have stretched 1/2 a millimeter. So the answer is going to be D. Question 5 is D. And even if you couldn't exactly remember what the pitch was, I would hope that you could, think through it and arrive at that answer. Question 6. Okay, so we've got some sort of sine wave. This could, most likely an alternating current, because we've got voltage over here and we've got time over here. So it's alternating back and forth and at some voltage at some time interval. So the voltage setting is 3 volts per division. So that means each of these divisions here, these boxes, is going to be 3 volts. And peak to peak voltage is the voltage from one peak to another peak. It's peak to peak voltage. It's very literal. So how many divisions? 1, 2, 3, 4, 5, 6 divisions. Each division is 3 volts. So 3 times 6 is going to be 18 volts. So question 6 is D. Question 7. So it's saying that given the time setting is 1 millisecond per division, so each of these boxes in this direction, we've got time written down here, each of these is 1 millisecond. And hopefully you can remember what frequency is. If not, you've got a cheat sheet. So frequency is 1 over the period. Oh, what's the period? I don't know. It's problematic. You can also hopefully you remember what the period is. So the period is how long does it take to complete one cycle. So one, up and one down. That would be a cycle, right? So if you knew that that was the period, you could go, okay, how long does it take to do that? It takes 1, 2, 3, 4 milliseconds. So frequency is equal to, what's the formula again? 1 over the period. 1 over, let's just write P for period. Is equal to 1, 4. Right, but the period is always given in seconds. So how many milliseconds are in a second? Well, hopefully you remember that there are 1,000 milliseconds in a second. So this is, that's 1 second. Sorry, let me just wind back a little bit. That's 1,000 milliseconds. It's equal to 1 second. 1 second. So if we want 0.004 milliseconds as a second, we're looking at 0.004 seconds. So we would put 0.004 down there. And if we punch that into a calculator, which you'll bring to the exam, you'll get 250 hertz, right? That's one way of doing that. I actually find that to be sort of the long-winded way of doing it. Well, not the long-winded way. It's not the most intuitive way for me. So I think to myself, all right, there's 1,000 milliseconds in a second. It takes 4 milliseconds for this to do 1 cycle. So 4 milliseconds for it to do 1 cycle. If I want to know how many cycles in 1 whole second, which is the frequency, I can divide 1,000 milliseconds, because that's a whole second. So 1,000 milliseconds, I can divide that by 4 milliseconds, and that will give me the same answer. 250 hertz. And that's the way that it just makes more sense to me. It's more intuitive. Use either way, that's fine. Just remember that if you want to work with the period, you need that time must be in seconds. Yeah? So that means it's probably going to be a decimal. Okay. Question 7. Question 8. So question 8 is about logic gates. Now, there's 2 logic gates here. And what are they? Well, I always remember the 3 types of really basic logic gates with almost like a little word trick. Because if you remember one logic gate of the 3 basic ones, the not, the and the or, and you can really sort of infer the rest. And the one that I always remember is that it's D for and. And if I know it's D for and, then I can remember that that's a not gate, and that is an or gate. Yeah? So that helps me immeasurably. And then this little circle on it means that it is a not and gate or a NAND gate. And what a NAND gate does is it's an AND gate with a NOT gate after it. Yeah? So what would normally happen in an AND gate and a NOT gate? An AND gate, both of these inputs have to be high for this output to be high. Yeah? So if one of these is low, the output is going to be low. Okay? Or if both of them are low, the output's going to be low. But then what a NOT gate does is if the input is low, the output is high. So if this was a low here, that would be a high. And if this was a high, so high, high, high on the output of the AND gate, that would be a low on the output of the NOT gate. And this is really, a NAND gate is, well, that's a terrible drawing of an AND gate, but it's just both of those things together. Okay, so what does that mean for us? It means that any situation where one or both of your inputs are low, the output is going to be high. Okay, so I might just draw this out, because you could scribble all over this thing if you were actually working on the exam. So I might draw the whole thing out. So there's our first NAND gate, and that goes in, it just branches off, and that goes into our second NAND gate. Again, sorry for the terrible drawing. So let's think about this scenario. So low equals, so any low here will equal a high over here. So any low over here will equal a high over here. And that's a high. If that's a high, then that's going to be a low. So any high at this point will then equal a low at this point. Any low at this point would equal a high at this point. So, which one of the following logic gates can replace the two logic gates shown above? Is it an OR gate? So an OR gate is when either is high. I just realized I got to do something. Sorry, I'll be back and we'll finish this question later.